All right, welcome grade 10s to our class for today, where the topic we're going to be having a look at is a brand new topic called vectors and scalars. Now, vectors and scalars is located under the main heading of, sorry, let me just fix that, of mechanics. So the first thing we have to ask ourselves is, what is a vector? And also, what is a scalar? So we begin by first defining what a scalar is. Okay. Now, scalar can be defined in a number of ways. It can be defined very short, in other words, shorthand, or using very few words, or we could have a very long explanation for it. Okay, either way, it doesn't matter. You just need to answer your definition question in a test or exam based on the mark allocation. If it's a 2-mark definition question for 2 marks, then you know you don't need to say a lot, but you need to cover the main points or the highlighted points of what a scalar actually is, because scalars and vectors, they are, at the end of the day, different things. So what makes a scalar quantity a scalar quantity? Well, first of all, we must understand, I've just given a bit away, that scalars and vectors are physical quantities. So a scalar is a physical quantity. I'm going to give a little bit of the long definition first. It's a physical quantity. All right? That has numerical value. Alright, numerical value and a unit. Okay, the scalar is a physical quantity that has a numerical value and a unit. Okay, now we call the numerical value with its unit the magnitude of the quantity. Okay, so numerical value, all right, and its unit is called the magnitude of the quantity. Okay, so often when we see in a test what is the magnitude of a certain and whatever they're asking for, right? What is the magnitude of the runner's speed, or of how fast the runner is running? What's the magnitude? What's the magnitude of the force, for example? Or what's the magnitude of the what's the magnitude of how heavy is the bag, how heavy is the brick? Magnitude refers to the numerical value as well as the unit. Examples of scalars, okay, or scalar quantities include time. How do I know that time is a scalar? Because it's measured in seconds, and it can have a value, 60 seconds, 30 seconds. All right, also measured in minutes. Time can also be measured in minutes, so 60 minutes, 30 minutes, 15 minutes, and also hours, 1 hour, 2 hours, 3 hours. Okay, days, right? Some of you may not know, may not or may not register this as time, but a day is also considered to be a way to tell time, or way to bring across time or show time, because a day has 24 hours. All right. So time is a scalar, as well as mass. Okay, now mass is how heavy a person, an animal, or an object is. Okay, example, me sitting here right now, I'm about 90 odd kilograms. I'm about 93 kilograms. I'm about 93 kilograms sitting here. Okay, so that's quite, that's my mass, right? We get it wrong as human beings when we talk especially when we use English or just normal everyday life. When we talk about this, we talk about weight. Okay, but weight is actually not a scalar quantity. Weight we're going to talk about in just a few moments. But mass is a scalar quantity. In other words, it just can have a value, a numerical value, and a unit. So in brackets here in physics, time is measured in seconds, so I'm going to use S for seconds. Mass is measured in kilograms in physics. Okay, so in physics, when we're doing any calculations that involves mass, we must use kilograms and not grams. Time as well, we cannot use minutes, we need to use seconds. Another one, which is speed. Okay, speed is also calculated in meters per second. Okay, how fast someone is. And then as well, lastly, distance. Alright, and we know distance in physics is measured in meters. Okay, awesome. That is what a scalar quantity is. If we move down to vectors, right, vectors is cousin, right? Now vector again is also a physical quantity, right? But the difference here, okay, is that a vector is a physical quantity that has magnitude, all right? That has magnitude and, big word here, direction. Okay, so magnitude, which I misspelled initially, all right, can we see the link here? So magnitude, meaning it has a numerical value, it also has a unit, except now we are using or adding direction into the mix. If I indicate direction, I have a vector quantity. All right, let's have a look at a couple of examples of vectors. Examples of vectors include displacement, right, which we'll talk about in a few more moments. Displacement, all right, which is also measured in meters. Okay, velocity. Velocity is also measured in meters per second. Acceleration, which is measured in meters per second squared. All right, meters per second squared is your acceleration. And then, see if I'm missing out any. I want one more, and of course, force. All right, which is measured in newtons. Okay, now something that's similar to force is weight. All right, W, which is weight. Okay, actually it's small w and not capital W. So weight, okay, is also a force. Is calculated by taking the mass of an object times the gravitational pull or times gravity of the object, right? And this is also measured in newtons. So weight is also a force. So weight is measured in newtons. So if someone technically in the world of physics, if you're talking about someone's weight, you're not talking about their mass in kilograms, but you're talking about their mass in kilograms multiplied by the gravitational pull of the earth, or multiplied by gravity, which is about 9.8 meters per second squared, and that gives you the person or that object's weight. So now that we know the difference between scalars and vectors, the next thing that I need to teach you is that we can actually represent vectors. Okay, and the way we do that is that we represent them, all right, using arrows. Okay, now when you use arrows, okay, as such, okay, in the example, draw an arrow like this. Okay, that obviously indicates direction. Arrow is a very good tool or graphical representation to show direction. Okay, so what do we do is that the length, okay, So I'm going to use a bit shorthand notation here. So the length of the arrow, okay, what does this do? What does this represent? The length of arrow, it represents the magnitude of the vector, the size, the numerical value. Alright, so it represents the magnitude of the vector. Okay, and we draw them. We usually draw, alright, we draw vectors to scale. Okay, for example, those who are watching and those who are attending, for example, I can have, because in an exam I'm going to have a ruler with me, so I can say, well, 1 centimeter on my ruler is equal to 10 meters in real life. Alright, so if in my scenario I am told that someone walked 10 meters, alright, or someone walked, not 10 meters, sorry, someone walked 50 meters, then I know I need to draw a 5 centimeter line because I multiply my scale by 5 to both sides. Okay, so that means 50. So that means therefore, if someone walked 50 meters and I multiply both by 5, then 5 centimeters needs to be the length of my arrow to represent the walk made by someone or walked by someone that covered 50 meters. Okay, that's just for example. Now that's the length of the arrow, or the body of the arrow, which we see over there. Okay, what does the arrowhead represent? Okay, so the arrowhead, okay, the arrowhead, alright, is drawn in the direction of the vector. So it indicates the direction. Okay, it indicates the direction of movement. Right, indicates the direction of movement. Okay, so there is more than one way to represent a vector. Okay, there's more than one way to represent a vector. So what I'm going to do is just show you again, or point you to the Siyavula textbook, which I'm going to be making use of, looking at the graphical representation. Okay, which I've already taught this section already now, showing you the different ways that we can obviously describe a vector with the arrows, etc., explaining that the length shows the magnitude, and the part where the head is, the arrowhead, so this part here, that's the arrowhead, and at the end of it is obviously the tail of the arrow. Directions. Okay, now we've talked a lot about directions. We know vectors has direction, yes, but there's more than one type of direction that we can use to represent a vector, for example, in given scenarios. So relative directions is the first type, okay, as indicated here in the Siyavula textbook for grade 10. These are your directions, in other words, forward, backwards, to the left or to the right, up and down. In other words, there's no real specific compass direction on it. Okay, it's just normal everyday directions. Go left, go right, go forwards, go backwards, go up, go down. That's called relative direction. So if there's no compass direction given in the scenario, but you know it's either going forward or backwards, then you would stick to the relative direction that's given in the scenario for the question. Compass directions, which I've already just mentioned now. Compass directions, we know we have north, south, east, west, which are our 4 major compass directions that we have learned over the years. And there, of course, is more. There's northwest, southwest, northeast, southeast as well. Those are your normal compass directions. So what happens is that sometimes you'll be given a scenario saying that Johnny walked the Kalahari Desert 50 degrees north of west, and all you do is you draw this represents the surface, okay, if that's the ground, alright, or if that represents find out where north is. So if that way was north, okay, he's walking 50 degrees north of west. Okay, it's 40 here because they're looking west of north. Sorry, west 40 degrees north. Okay, which basically means he's 40 degrees off of north. Okay, and very seldom that you'll get something like that. I wouldn't say seldom. I would say it's not as often. It's probably going to become more often as we go along. But definitely I will try and do a live example with a compass direction of this magnitude, just to see that we can all understand it. We can all do it if we get it in a test or exam. But those are your normal compass directions. So if you know it's going north, if you know it's going west, you obviously make use of those compass directions in your answer. Okay, and then we have bearing. Okay, now bearing is very interesting. For those of us that do geography, you should know bearing very well. All right, it's included in map work. Okay, sorry about that. Now bearing is a direction relative to a fixed point. Okay, so if we have a look at an angle, we get given an angle, so we'll take the angle that is given in the textbook just to see if we can make sense of it. So given just an angle, the convention is to define the angle clockwise with respect to north, of course. So we're always finding the angle with respect to north. So vector with the direction of 110 degrees has been rotated clockwise 110 degrees relative to north. Okay. Now a bearing is always written as a 3-digit number. Okay. So when you are even when you have a bearing and it's only a double-digit number like 80 degrees, you still need to write it as 080 degrees. That is for only when you are required to calculate bearing. Okay, but it's always written as a 3-digit number. So when it comes to representing and actually drawing vectors, what we need to do is we need to make sure that we know, number one, okay, we need to understand and write down our scale that we are working with. Okay, so for example, I got 1 centimeter. That represents, for example, 20 meters in real life. Okay, that's obviously dependent on the scenario that you are given. Okay. Then number two is you need to decide on your reference direction or your reference point. All right. You need to obviously decide upon that. All right, you need a reference point. And then number three, what you need to make sure is that you obviously need to draw the length of the arrow. You need to draw it, the length of the arrow that's representing the vector. You need to draw that according to scale. Okay, so if it's according to that scale, it needs to be drawn according to that scale. Okay, you must add, for number 4, add in the arrowhead or the arrowheads. Alright, on all of your arrows. Okay, and that's the major points that you need to do with regards to drawing a vector. Always you need to make sure that all these points are, of course, obviously covered. So for example, if I have a scenario, I have A and B, so I have two objects. Okay, so, or rather let A and B be defined for tracking the motion of a certain object. So if the object walked in this direction, right, and this is A, alright, I need to include my arrow on top as well, arrow showing that it is going in this direction, and the length here of this arrow indicates the vector that is actually going in this direction. Then it changes direction, for example, from after it reaches this point, it changes direction and it decides to go this way, an upward direction. Okay, but it's still moving forward. Okay, and this little arrow on top here just indicates that it actually is a vector quantity. Okay. Then if they ask you for something that is called the resultant, all right, or the resultant vector. Okay, the resultant vector in this case, if we have a look at this little diagram here, the resultant vector is going to definitely be this line over here. Okay, this line, because this dotted line here represents the vector A plus vector B. Okay, that would be the resultant, all right, vector. Okay, so the resultant vector is just taking either the addition, all right. If they're both moving forward, then we know that we have to choose which motion is also your positive, all right. So with your reference point here, another point here that you need to determine which motion or which direction is also positive, all right, which we'll have a look in a real actual example in just a couple of seconds. Okay, and then the resultant is basically the net, all right, the net vector magnitude and direction. That's your resultant vector. So looking at the first example here out of the Siyavula textbook, having a look at a textbook example before we look at another one, all right. They ask us to draw the following vector quantity v with the arrow on top, meaning that it has direction. So it's a vector, so it's not v for speed. Sometimes v is also used for speed instead of s. Okay, but v with a direction arrow on top indicates it's the vector velocity. All right, equals 6 meters per second north. So step one, what we need to do, decide on the scale, and we need to write it down. So I've decided, or they've decided, use the scale at 1 centimeter equals 2 meters per second. All right, and that's a good scale because 6 is a multiple of 2. All right, 2 times 3 is 6, so that means only 3 centimeters will give me 6 meters per second according to the scale. Okay, you need to decide on your reference point. Okay, and my reference point is north. All right, north is going to point to the top of the page. Right, that's my north. All right, bottom of the page will be south. Okay, and left, right is going to be respectively east and west. Now step 3, we need to determine the length of the arrow. Okay, which I did very easily. If 1 centimeter is equal to 2 meters per second, then I need to get to 6. So 2 times 3 is 6. So then 3 centimeters is going to equal 6 meters per second. And then I use my scale. I indicate the direction, north. That line is about 3 centimeters, 6 meters per second. I've indicated direction, going northerly direction, and as well as the numerical value and unit. Okay, I've indicated the magnitude of the vector as well. Right, very good example. All right, the next topic we're going to move on to, still within mechanics and under vectors and scalars, is motion in one direction. Okay, or motion in one dimension. And we're going to have a look at 3 terms here. We're going to have a look at frame of reference. Okay, we're also going to have a look at position, as well as displacement. Okay, but displacement is also around distance as well. Okay, displacement in terms of distance as well, because distance and displacement are cousins as well. One is scalar and one is vector. So if we have a look at the first one, frame of reference. Okay, frame of reference. Awesome. All right, which is sometimes also called reference of frame. Okay, this is a context. Okay, it is a context against which the motion or position of an object is defined. Okay, so with a frame of reference, okay, it has an origin, okay, starting point, okay, it has an origin as well as set of directions. Okay, it has origin as well as set of directions, which are usually represented by the x and y axes as well. Okay, but that is frame of reference. Okay, then we have another term similar to frame of reference, which is called your reference point. Okay, now your reference point, first of all, this is the point in respect to which we measure distance as well as position of an object. Which moves into the next point, which is called our position. All right, with position of an object, that is the point where the object is found, okay, at a certain point in time, okay, and it would be measured, all right, relative to a reference point. Thus it is a vector. Okay, so the position and reference point go kind of hand in hand. Okay, I want to have a look at something that's called displacement and why it is the cousin, or I just call it the cousin. Okay, displacement, the cousin of distance. Okay, now displacement, we know distance, well, speaks exactly for itself. It is the distance. Okay, if I walk from my house to school and I want to know how long that is, or the distance between my house and school, I can measure it, of course. Okay, that's just the distance. If it ends up being 12 kilometers, then it's 12 kilometers. Neither here nor there. 12 kilometers from my house to school and 12 kilometers back from my school to my house. But displacement of an object, okay, is the object's change. Okay, it is the object's change. Sorry, here we go. It's the object's change in position. Okay, in other words, it's this change in position, okay, from starting point, okay, change in object position from a starting point to its final position or finishing point. Okay, in other words, if I went 12 kilometers north, then I went back, or I went 10 kilometers east, and then again I went 12 kilometers south, and then back 12 kilometers north. Okay, I'll ask what is the displacement. Okay, I'd have to choose which is my which direction I'm choosing to be positive and which I'm choosing to be negative. Okay, but we'll explain that in just a second. Okay, so in other words, displacement delta x basically means the final position xf minus the initial position xi. So for example, for displacement, if I went 12 kilometers, right, in this direction, let me fix that up. I went 12 kilometers in this direction, so that's 12 kilometers, and then I went again 6 kilometers that direction. According to this formula, delta x would mean my final position, which was over here, okay, and I initially ended up here, okay, my final position was here, okay, that becomes my initial 6 minus 12, my displacement ends up being -6 kilometers, but that negative indicates direction, meaning it's 6 kilometers, and we can just say in opposite direction. So if we take a real example, okay, let's take an example quickly. Okay, very theoretical, gonna try and make it up along as we go. Let's say we have a car, okay, and a car travels 80 kilometers to the east. So car goes 80 kilometers east, okay, and it goes from position A to position B. So let's figure out a position here. So let's say this is position A, and then we have position B over here. So if I have a car, that's my car, and I go all the way from there to there. Okay, here we go. Cool. And that's 80 kilometers. Okay. So there we go. That's my drawing. 80 kilometers. And then I turn around and I travel another couple kilometers. Let's say I turn around and I end up at point C. So the car then turns around and ends up, let's say, about here. Okay. Also, I need to indicate that it's going like that. That's 80 kilometers there. From here to about here, that's 50 kilometers. Okay, and that's C, point C. Okay, and west is in this direction. Okay, because it's going east, so it must be coming from west. East is over here. Now they say find, or let's keep it simple. Let's calculate the distance. Okay, now keep in mind distance is a scalar quantity. Alright? Distance is a scalar quantity. I've kind of mapped out the vector already, so I know it's going 80 kilometers from west to east, going in an easterly direction, and then it turns around and goes back in a westerly direction again. Okay, but I want the distance. I don't want anything else. I want the total distance. Okay, so distance, when we're calculating distance, all we're doing is that we just add all the distances. Okay, in this case he went 80 kilometers and then he went another 50 kilometers. So I want just the total distance that he traveled. Okay, so in this case it's going to be my 80 kilometers plus my 50 kilometers to get the total distance that he traveled. That's all. Right, it's really not that difficult. Okay, so let's try that. Okay, I've got 80 plus 50, which gives me a total of 130 kilometers traveled. That's just distance, right? Now distance is pretty easy. But now what happens if I ask, now I want to know what is the final displacement. Now I'm looking for delta x, which we know is the final position minus the initial position. Alright? So I ended up, my final position was at point C. Right? When I traveled, I got to an initial position at point B. Okay? So, to find my displacement, my final displacement, okay, I need to look at the initial position. Okay? So, the initial position was from A. Alright? Even though I ended up at B, after I traveled from A, my initial position is actually at point A. Okay, because that's where I began. And I wasn't moving at point A. Okay, I wasn't moving at point A. I moved from A to B and then from B to C. Okay, point A is at the origin. All right, where I began my destination. Okay. So what I got to do, okay, I've got to find out what is my final displacement. My final displacement, okay, which is basically 80 kilometers, all right, or should I say rather, because A's distance was 0 kilometers. So if xi represents A, I'm not moving, it's 0. Notice that at point C, from B to point C is 50 kilometers. So if A to B is 80 kilometers, and from B to C is 50, then the distance from A to C must be 30 kilometers. So my final position, if A is my origin and my point of reference, then my final position must be 30 kilometers minus 0, which means I just get my displacement to equal 30 kilometers. Okay, and if I add a direction, okay, my direction is 30 kilometers east because I have a positive number. All right, I don't have a negative number. Okay, I still have a positive number because looking at my vector over here as well, from B to C, if C ended up past A, I would have had a negative number because B to C, if C was over here, would have been longer, all right, a greater distance from as compared to from A to B. But because B to C was only 50 and there was still 30 kilometers from the final position to my initial position, okay, I do an analysis where I draw the line and say, well, if there's 30 kilometers left from point A to point C, then that means that obviously is the distance from my final position to my initial position. Therefore, all I do was take 30 minus 0 to get 30 kilometers east. And that was the final displacement. But now what happens if we get a question that says find the final displacement of the car or object, okay, but with respect to point B, okay? Now this is a bit of a different scenario here, okay, because now our reference point is point B now, okay? So this is for if you get a third question, our reference point is now point B. Alright? The initial and final positions would have to be points B and C respectively. Okay? So if I have my displacement formula again, delta x is equal to my xf final position minus my xi initial position. Okay? We know that at point C was 30 kilometers. Okay, because that's where I ended up, right, at 30 kilometers, at the 30 kilometer mark. Okay, so 30 kilometers minus, and at point B, what was my distance? My distance was 80 kilometers because from A to point B, okay, is 80 kilometers. So I'd have 30 minus 80. If I do that, I end up with negative 50 kilometers. Okay, negative 50 kilometers, and this negative indicates a change in direction. So therefore my final answer would say delta x is equal to 50 kilometers due to west. In other words, it's going in a westerly direction and not in an easterly direction. And that is all we have time for today. Thank you so much for joining me on my lesson on mechanics, looking at vectors and scalars, looking at how to represent vectors and how to understand these scenario questions, especially with one-dimension drawings and scenarios. We will see you next week again when we'll look at more calculation-based questions under vectors and scalars.